This conference will now be recorded.
Online, whether it's
Good
audible.
morning, sir.
Yes, very
Yes,
good
sir, it's
morning.
audible.
Yes. See, today here we are for physical design demo. Screen is not sharing, right? Yes. Very, very good morning to everyone. Right. Today we have PD demo. Now, before going to PD demo, right, I will tell the highlights of the institute beginning, right? Because what I want to do is instead of going to the demo directly, because some students, some will be having their work, they will leave the demo in between. So first I'll tell the highlights of the institute, right? So what is the, see later you can ask the questions after we complete the demo. Demo will be for 3 hours. Demo will complete at 12:30. Later you can ask the questions or you can ask the questions now itself. So right. So later I will start a technical part. So first I will go through the highlights of this course. Right. See, here we have two courses. One is basics. One more is PD advanced. Right? So in basics, what is that? In basics, right? We are going to teach digital because digital is very important for all the backgrounds. So you should be knowing what is flip flop, what is latch, right? What is asynchronous design, what is synchronous design, right? What is clock, how clock is going to affect the operation of flip flops. So those things is very important for physical design. So second thing is you want Unix, right? So for everyone, for the normal student, Unix is new. So there is an operating system called as Linux operating system or Unix operating system. So we can interact with the operating system by using Unix commands. So Unix, all the EDA tools are installed only in Unix operating system. Generally, we use Unix to install all the operating system tools. So Unix has its own special features. So in the Unix, we can create the groups. Only for those groups we can give the license. So for that reasons, right? All the companies use Unix as operating system to give the EDA tools for all the engineers. So for that reason, you should be learning what is a Unix commands. So till now, I am seeing in the current industry trends, even with 3+4+ years experience, they don't know what is a command to copy one file from one location to another location. So we have in-depth Unix class done, right? So after learning Unix class, you can use any command what is present in the operating system, except few commands like grouping, create grouping, and you need not to worry about that. The server management will take care about that, right? So next is third thing is TCL. TCL stands for what? Tool command language. So why this is important? A tool command language. See, EDA tools, electronic design automation tools, can understand only TCL. They cannot understand other languages. They can understand C, C++, or Python. They can understand only TCL. So if you want to interact with EDA tools, EDA tool stands for electronic design automation tools, which we use to do the circuit design. For example, everyone have used your Xilinx for FPGA design in your UG classes. So how many of you have interacted with the Xilinx by using TCL? No one, right? If you learn TCL, you can automate the design. So industry uses automation flow. Every industry. You take Intel, they have automated flow. You take Qualcomm, they have automated flow. So every automated flow is developed based on what? TCL. So understanding tool command language is very, very important, especially for physical design. Next is you should be knowing CMOS. So next we'll do CMOS basics. After that, see in CMOS basics, what is important? What is PMOS? What is NMOS? Which you already know, but still we'll revise it. What is NMOS? What is PMOS? What are the issues we see in NMOS and PMOS? What is CMOS? Right? In CMOS, what is layout and what are the characteristics of CMOS? Like how to determine its speed, how to determine its transition time, what are the different power, what are the different types of powers in CMOS? Why we are not using CMOS or MOSFETs below 14 nanometer technology? Why we are using FinFETs? So all those things you learn in CMOS basics. Next is PD basics, right? Before going to physical design advanced, but some basic terminologies you have to learn. What is transition time? What do you mean by speed? What do you mean by power? It depends on what aspects. What is chip? What is flip chip design? Right, like that you have to learn few terminologies. So we have PD basics for that. And after immediately, see, this basics is for 2 months and advanced is for 3 months. So this is a planned schedule. Slightly it may get varied, like 15 days may get extended due to some various reasons, right? Because slow phase in learning or various reasons, max to max 15 days get extended. Like instead of 5 months we may take 5.5 months, like 5 months and 15 days maybe get extended, right? So in advance, right, we use technology node 28 nm slash 14 nm. 28 and 14 we use. With one design we do it at 28, one design on 14. Right, you will learn all the aspects of physical design. See what you will learn, I'll brief in the next technical aspects. And main thing here, the projects. You will do the main industrial level projects. You will do two projects. So one project is done with the help of a mentor. So mentor will take the project session every day for 2 hours or 3 hours. Right. One project will be given to you, right, when you complete the course to practice it. Right. That is what. So advanced course is like weekend theory. Weekend you have only theory from the industrial experts. And weekdays you have the project. This project will be done for on weekdays. Even you have option to switch to weekend projects also. You have two things. See, theory is on only weekends. Theory is on only Saturday and Sunday, but project will be done on weekdays, Monday to Friday or Monday to Thursday. Friday is holiday. Monday to Thursday project. Saturday and Sunday is the theory sessions. But if you cannot attend the weekdays projects for various reasons, you're already working some reasons, right? Then you can opt only for weekend projects. Weekend projects are different, weekdays projects are different. You can opt any one thing. Either you can opt weekdays project or weekend project sessions. That will be done for 3 hours every day with help of a mentor, right? So this is what the highlight of the course. Now, when we come to the additional benefits, what you will get, right? You will get the recorded videos. Recorded videos means, see, not pre-recorded videos, live recorded videos. For example, today I have done the class. I have done the project class on Monday. You were not able to attend for several reasons, your own reasons. Then, if you attend Tuesday, you will miss the continuity, right? Then we will give the Monday's video, everyday video for next 15 days. You can watch whenever you have time. Like Monday, you went somewhere during the class hour, night you came, you can watch the video and you can get back to Tuesday's class. So we will give the recorded videos. The videos will be there for 15. This is a live recording videos, not the pre-recorded videos. Live running class recorded videos. Live recorded videos for 15 days. So tool access will you. The tool is very costly. First of all, I'll mention this. Right? Tool license is very costly. I don't want to mention what is the cost for industrial perspective. I will mention the academic. For academic, it is more than 10 lakhs. Okay, I'm talking for academics, means for college levels. It is more than 10 lakhs for 20 license. So tool is very costly what we are using here, because these are the EDA tools which has to mimic what is happening in real silicon, that they have to mimic in the software. So for that reason, tools are very costly. So this tool, whatever we are using for physical design, you will get 24/7 for 3 months. This 3 months till the project get completes. Starting of the project till the project it completes. After project completing, the tool access will be extended for next 15 days to practice. For example, if today project completes, so we are giving one more project, right? To do this one more project, we will extend the tool access for next 15 days. So tool access will be there for 24/7 till project completes, plus 15 days. This tool access is removed only for the online students. But if you come to institute, right, you can access any day. You can access even for 1 year. But if you can come to the institute, in institute tool access is not removed. Only VPN is removed. VPN means accessing from away from is removed. But when you come to the institute, you can even access the tool. See this till project completes, you can access from anywhere. This period, project completes the 15 days, you can access from anywhere through VPN. 3 months plus 15 days. After 3 months or 15 days, again, if you want to use the tool, then you can come to Institute and you can use the tool with our Wi-Fi. Right? This is a facility what is given. And about placements, I'm telling this in the beginning only because later you should be having any question, you can note down and you can discuss at the last. So when I talk to the placement, say nowadays the placement of physical design is very good. It's excellent placement, right? And most of the companies who want the freshers, they will approach us. Even who want the experienced candidates also will approach us. VLSI Guru. So because they are already having the trend to approach the VLSI Guru from the beginning. So they approach us if they want any candidates. So when they are approaching us, we will intimate to the candidates who have completed their course. We'll pick the resumes and we'll forward to the respective companies. But before sending your profile to the company, we will make you ready with mock interviews and test. We will be during this course, right? You will be having regular mock interviews and test. Because when your profile is sent to company, you have to clear the interview. If you are rejected, again they will not allow you to take the interview for next couple of days. So when you send it to the company, you should clear the interview. So we will take couple of mock interviews. So when you are clear those mock interviews and the test, right? You're done good, then we send you your profiles to the company. And I'm damn sure, right? Even I have done the course in VLSI Guru itself long before in the 2019. I'm telling this openly. If you are serious about the course, you will surely succeed. But only I use only one word. If you're serious about the course, you'll succeed for sure. You'll end up with earning more than a lakh within couple of years, 1 or 2 years. But if you want, you should be about serious about your course. Say coming for 3 hours, listening to the mentor, going back, again coming will not help you. You should work out something. If I teach TCL today, you should work on the programs what we have taught. You should do the assignments what we are given. So you will develop a good knowledge and you can crack the interviews and you will grow fast in industry. So this course will not only help you to the getting job, it also help you to grow in future. Because I am repeating this word again, the person with 3 years of experience or 4 years of experience doesn't know how to use Unix or TCL. I'm telling this statement openly. If you prove me wrong, right, it's okay. That I'm telling you. So if you focus on this basics aspects properly, then you this will not only help you to get into the jobs, this also help you to grow in that field. This is the highlights of the complete course which are done at the beginning itself, because most of them will because others will be having some work, they will leave in between. If you leave in between, you can have a glance on this highlights of the course and whatever I told. So I'll give just 5 minutes, right? If you have any doubts, you can ask me.
You mentioned about the class being not on Friday. So is it leave on Friday? Is it off on
Yes,
Friday?
off on Friday. See, the projects, right? This project will be done on Monday to Friday, Monday to Thursday, sorry, Monday to Thursday. Or you also have an option, right? You can opt for Saturday and Sunday, because some candidates will be working already. They can opt for what Saturday and Sunday. This basics will go for all the days, because a person who is already experienced, like he's already having some teaching experience or some other experience, they don't want basics. They can go through the videos also. A person who is capable of self-learning. So this basics is for all the days, from Monday to Saturday, and Sunday is off. And when you go to advanced part, projects will be running from Monday to Thursday, or you can also take till from what Saturday and Sunday. It's optional. And theory will be done only on Saturday and Sunday. Theory means conceptual wise, floor plan. What are the important topics? What are the important concepts in floor plan? That will be done by the industrial experts. Yes, this is about the thing. And here, the persons who are attending on Monday to Thursday, right? They will also attend what? Theory. So, where do you see the leave? Leave on Friday. This theory is for all. Those who are opting for Monday to Thursday projects, or for Saturday and Sunday projects. Saturday, see, morning there will be a theory, afternoon there will be a project or lab. So, if you attend this lab, you need not to attend this. Here, so I see, if you have the question which is better, I suggest attend Monday to Thursday, but because you will be having more days to work. But if you are not available, then you opt for what? Saturday and Sunday. Any doubts you have? Online, any doubts you have? So why we want physical design, right? So today's agenda is to give the highlight of the course. First thing I've already done. It is a major agenda, highlight of the course. Second thing is, right, many will be freshers. They don't know what is physical design, right? The second agenda is what is Physical design. Right? What is done in physical design? Done in physical design. See, what is physical design? Instead of that, I can use what? Why physical design? Why this physical design course, or why this physical design process is done? Then what is done in physical design? Right? And the course content. Here I didn't mention what is the course content in the second part, but I'll cover here in the technical part. So next my agenda is next for at least 2.5 hours. Next my agenda is why physical design, what is done in physical design, and what is our course content. This is my next agenda of discussion. And in that one of the agenda is course highlights, which I've already told. These are course highlights. So next we will go to why physical design. See, why we are doing all these things, main agenda is for IC fabrication. Our main agenda is what? IC fabrication. You know what is IC, right? Integrated circuit. I think everyone has seen the IC. So IC fabrication is done where? Where IC fabrication is done? Can you tell me where IC fabrication is done? See, IC fabrication is done in a place called as foundry. Foundry is a place where the IC fabrication is done, and in the foundry, the major role is for chemical engineers, not for electronics or design engineers. Because in the foundry, the IC is fabricated by a process called as etching, vaporization, right, oxidation. After that, they'll do etching, ion implantation, diffusion. So all this process will take through chemical process. That is not a electronic process, I can tell, right? So mainly who are going to work in fabrication unit or foundry, nothing but chemical engineers. So role of electronics engineers are very less in foundry. So mainly the chemical engineers are going to work in foundry, right? But foundry is a place which is, it should be highly sophisticated, right? Highly sophisticated. So minimum you require 500 crores of investment to open a foundry. See, foundry should be very clean, neat, right? And even a small chalk powder, you know, right? That may cover hundreds of transistors because transistor size is in nanometer, right? The transistor, you know, transistor size is in nanometer. Nanometer means, you know, right? Everyone knows this because scale is in millimeter, the smallest unit in scale. When you say the smallest unit in scale, that is in millimeter. If you divide that millimeter into 1 lakh times, then you will end up with what? Nanometer. Then even you cannot see through your eyes. You need some electronic microscope to see these transistors. So if a chalk powder falls on this fabrication unit, that may cover hundreds of transistors. So the fabrication unit should be like even 10,000 times neater and cleaner than the ICU or operation theater what we have. That is a requirement for a foundry. So it requires huge investment. So when any company want its IC to be fabricated from foundry, right? Even they have to invest in huge. For example, Qualcomm wants its IC to be fabricated. Even they have to invest in huge. For example, they have invested some 50 crores of money to get their new IC to be fabricated from foundry. When that IC comes to market, right, what is the cost? Not more than 2000 rupees. In mobile phone, whatever we are using IC, it is not more than 2000 rupees. less than 2000. So all the cost like battery cost, everything, it will around 10,000 or 12,000. But IC cost will be just for 2,000 rupees. Advertisement, everything covers for 12,000. IC cost will be to means to meet this investment, right? How much IC they have to sell in the market? They have to sell in crores. Then only they can meet their investment. Any company you take, see there are many product-based companies called as Intel, Qualcomm, AMD, Nvidia, MediaTek. Right? There are many product-based companies who sell their ICs for various applications. Qualcomm sells for what? Qualcomm is going to sell for mobile phone applications. Intel is for PC, laptops, and servers. Right? They create CPU, GPUs, ICs for these things. So when this ICs come to the market, right, they have to hit the market for any reasons. If they are not hitting the market, they are going to suffer a huge loss. When this IC has to be hitting the market, means IC should be very good in terms of area, power, and speed of operation. If anything is failing, right, the IC is lost. Then who is going to design this IC? Right? There is a thing called as designing an IC, design IC design. IC design is done by electron VLSI engineers. So we are going to do the IC design, right, by using EDA tools. What are EDA? What is the full form of EDA? Electronic design automation tools. So we use EDA tools and we are going to design an IC. Means we are going to use a software to design an what? IC. This EDA tool should be mimicking, they should mimic what is happening in the real silicon. All those things they should be mathematically model, and that we use that mathematical model to what? Design an IC. Right? So now, what this foundry will understand from the IC design team, what we give to the foundry when the circuit is ready, when VLSI circuit is ready, what we give to foundry, so that foundry is going to fabricate our IC. For example, you take one example, Qualcomm is ready. Qualcomm is a design team, that is not a fabrication team. So Qualcomm is going to fabricate the IC from some foundry like TSMC, Taiwan Semiconductor Manufacturing Corporation. What Qualcomm should give to the foundry so that foundry will give the IC for us. What we should do?
Code.
No, what is that called as? Not not code. Can anyone tell me what we should give to foundry so that foundry will give us the IC fabricated? We are IC design engineers. For example, you assume that you have done the FPGA design. At last, what you created so that your FPGA start working like IC.
GDS.
Good, right? You should use GDS. In FPGA also, you have created on bit file. At last, you will create on bit file. That bit file will dump on FPGA. So your FPGA will start working as IC. FPGA is reusable, but still FPGA is reusable. Why we go for this method? This is called a cell-based method. Why we are not going for FPGA method? Everyone know what is FPGA, right? In music classes, you have used FPGA. FPGA is reusable. You can reprogram the FPGA. If you dump the program for D flip flop, it will work for D flip flop IC. If you dump the program for counters, it will work as counter IC. Then why you want to go by this method?
We have product from
FPGA, only reason is FPGA is not in a designer control. Already IC is already present. We are only taking care of connecting the internal modules. We are not responsible for creating the modules. We don't have that control. For example, I have small code. This is my FPGA. You assume I have some small code. That small code is occupying only this much resource, and remaining resources are wasted. Simply, I am using what unnecessary area. I have dumped a program for D flip flop. D flip flop will take how many? Oh, okay, I have dumped a program for 4-bit counter. 4-bit counter takes how many flip flops? Max to max 4 flip flops, and few combination cells like 50 combination cells. So only that much area I am going to occupy. and remaining area gets wasted, correct? All this area get what? Wasted. Means area I don't have control, right? Even timing I don't have control. I don't want this flip flop. I want to use some other flip flop. I don't have control because already the circuit is present, FPG. So when we want to have the better optimization, then we cannot use what? FPG. Because circuit is not in my control. Circuit is already present. Already circuit is fabricated. Only designer control. In the designer control, what is present? Only coding is present. Means only connecting the submodules is present in the designer control. Right? So FPGA is easy to program. So design phase is very fast. You can do FPGA design even within 10 days. Design phase is very fast. But the problem is FPGA is not in our control. FPGA circuit is already done. Only connecting the submodules is in the controller of designer. So we will not go for many times. We will not go for FPGA design. We will go for this ASIC design always. Right? So IC design team will give GDS to the IC fabrication team. GDS 2. GDS stands for graphical data stream information interchange. So this file is given to the IC fabrication unit. Then what this file consists of? This GDS consists of layout of cells. It consists of what? Layout of cells. I think in UG classes everyone is knowing what is layout. Yes or no? You know what is layout? Stick diagram, layouts. If
with
it is
only
not
metal
knowing,
layers.
no, layout I'll show you what is layout. If you're not knowing, then for that reason only we have what? CMOS basics. If not anyhow, we are going to cover it. Right? So layout means it is having the content like this. Right? This is the CMOS. CMOS has what? P substrate. It has N well. In N well, we are going to fabricate what? PMOS. In P substrate, we are going to fabricate NMOS. This, whatever we are seeing here, writing its top view. What is a top view? You can see that if you write, that is called as what? Layout. So layout has this. It is having a P diffusion. This P diffusion, and this green color is N diffusion, and this blue color is VDD. This is VSS. What is this? VDD. What is center thing? What we have? This polysilicon. This gate polysilicon. Right? And you know the structure of PMOS. What is structure of PMOS? If you don't know, for that reason only, I'm just pointing out why this CMOS basics is important, right? You have VDD. At the bottom, you have what? PMOS. Next, you have NMOS. That NMOS will connect to ground. Next, PMOS and NMOS will connect to gate. This is V in. This is what? V out. So this PMOS gate and NMOS gate, both gets what? Connected. Here also you can see this PMOS gate, this polysilicon is PMOS gate, this polysilicon is NMOS gate, both are what? Connected. And they are getting connected to this metal layer. Blue color is what? Metal layer. This blue color is metal layer. Right? So this both gate of PMOS, gate of NMOS connects to the pin called as V in. That is, pin means it's a metal layer. And next, what is that? PMOS is connecting to what? VDD, right? So here PMOS, this is nothing but PMOS source, PMOS drain. This is NMOS drain, NMOS source. PMOS source is connecting to what? VDD. So there is a connection happening. So NMOS source is connecting to what? VSS. So here drain and drain is shorting, right? Drain and drain is shorting. Here drain and drain is shorting, and it's connecting to what? Output pin. This is the layout of one inverter. This is a layout of what? One inverter. So only this information your foundry can understand. This only the layout of cells your foundry can what? Understand. So now you understood what is a foundry. See, who is going to fabricate IC? Foundry. Foundry can understand only what? GDS. In GDS, what is present? Layout is present. Then why physical design? Why we want physical design? To understand this, right? Why we want physical design? You want to understand this ASIC design flow. If I let the steps of ASIC design flow, right? It starts with specification. Okay, we'll go one by one. ASIC design flow starts with specification. So what is specification in industry? Industrial term, what is specification? Specification is nothing but, for example, if Qualcomm has to build one IC, right? First they want to see what should be my IC size, how much power it has to consume, what are all the blocks I should use in IC, right? IC will be having different blocks. If you see, your IC will be having like you will be having a block called as ALU, right? Memory, PCI, peripheral control interface, right? PCI, audio video decoder, right? Audio video decoder. So in total IC, what are the sub modules you want? What are the blocks you want? And each block is working with what clock frequency? What is the voltage they have to work? So all those things is decided from a architecture team, and the main business heads are involved. They will decide what is the IC requirement. In specification, we have IC requirement. What type of IC requirement? I told already. What is that? Number of blocks. Next, area, clock frequency. Next, estimated power consumption. All these things will be decided from the specification team. See, once this specification team decides what is the blocks we want, we should start implementing those blocks. This, right? This IC required all these blocks. Now I want to start writing. I want to start implementing the circuit of what? ALU block. One person will start implementing the circuit of memory block. One person will start implementing the circuit of PCI block. So what is that is called as a design entry. Design entry. So how this design entry will happen? Can anyone tell me? Yes. How this design entry will happen? So for design entry is also called as RTL coding. This stage. So in ASIC design flow, so we use HDL. Very good. Right? HDL means hardware description language. We use Verilog or VHDL to describe a circuit. We are using Verilog or VHDL to describe any circuit. So why Verilog or VHDL? Why we have to use Verilog or VHDL? Why I cannot directly write the circuit? Why I should describe through Verilog or VHDL?
Universal.
Now, why they started like that? Why they started using any programming language to describe circuit? See, because describing any circuit through its behavior is easy compared to its structure. So start the design, complex design, start describing through its behavior rather than its structure. Then we will come one step down later. First, start describing any circuit through its behavior. For example, I will give one example. Right? You know what is mux. Everyone know mux. What is mux? So you take 2:1 mux. So how many can you write the internal structure of the mux? How many can you write internal structure of the mux? Internal structure by using gates, NAND gates, NOR gates, or by using AND gates. How many can you write? Okay, no one cannot write. Or if you can write, okay, it's fine. Okay, you can write it. But you people are thinking about that. But okay, I will tell you what is its operation. Can you tell me? Like its behavior, can you tell me? Can you explain the behavior of this mux? Yes, I am getting the response, right? When select line is 0, my y is going to take what? I0. If select line is 1, my y is going to take what? I1. See, describing its behavior is easy, but describing its internal structure is very difficult. So when I can describe its behavior, I can easily use if statements, right? Use if statement. If s equals 0, what you do? Y is equal to what? Yes. Sorry, y is equal to I naught. Else y is equal to I1. So this is nothing but describing through programming language, right? This is syntax of Verilog almost. Not exactly, but almost syntax of Verilog. So describing any circuit through its behavior is easy compared to what? Through its internal structure. So what we do is every time we use Verilog or VHDL to describe the behavior of any circuit. So when we go to bigger circuits, like you assume that you are using bigger circuit, uh, you don't know I square C protocol. Okay, leave. Okay, you know everyone know ATM machine, right? ATM machine, you know how to write Verilog program for ATM machine. I want to write ATM machine operation Verilog program. How to write it? So when you think about at the bigger level, it's very difficult. Start thinking with different states. Right? What are different states you have? One is reset state. Always it should be showing one screen, like front screen. Right? That state I call it as reset state. So when input is zero, when no input is happening, when input is zero, my ATM machine will be always in what state? Reset state. When I get any input, like I get logic 1 as input, I'll go to next state called as logic 1 input. Means when card is inserted, then some intermediate sensor will generate logic 1 signal to my IC. My IC will push this into next state. What is the next state? Next state is pin entering state. If pin entering is not proper or pin entering is delayed, then my pin entering I'll output logic 0. Then I'll go to what state? Reset state. So this happens in two cases. One is pin is not entered at all for few minutes. Second thing is pin entered is not correct. Then I'll go back to which state? Reset state. But if pin entered is correct, then I'll go back to which state? Logic 1. I'll go back to which state? I'll go back to amount entering state. If pin entered is correct, I'll go to what? Amount entering state. See, display error and all, it's fine. That is internally we have to write the program. That is okay. So, but I'm telling only how to go one state to another state. If pin entered is wrong, then go back to what state? Reset state. If pin entering is correct, Pin is correct, then go back to what state? Amount entering state. If amount entered is wrong, like I enter 435 rupees, my ATM cannot give. Or I'm entering the amount more than the balance, then my ATM machine cannot give. Then at that time I'll go back to what state? Reset state. This zero is outputted. The zero is outputted only when the amount entered is incorrect or the amount entered is more than the actual balance. If the amount entered is correct, then I will go back to cash dispatch state. Cash dispatch state. So this cash is dispatched, right? Cash is dispatched, it's logic 1. If cash is not dispatched, it will be in this state only, right? Logic 0. If cash is dispatched, again go back to what state? Reset state. If not at cash is dispatched, then wait in the cash dispatch state. Right. So now this is the just I have written a small diagram. This is called a state machine diagram. So bigger circuit also we will divide into different states. Now we'll start writing the Verilog program to implement what each state. So bigger programs we generally start with bigger designs. We start implementing. See here also I am implementing the design by the behavior of ATM machine. How it is going to behave. So for this again I'll start writing the Verilog code to implement each state. So for that reason, right, we use Verilog or VHDL to do design entry because describing a circuit through its behavior is easy. So for that reason, we do design entry by using what? Verilog or VHDL. So here there is one job opportunity. This entire RTL design engineer, his role is to write the Verilog codes for any design, bigger designs, not for smaller designs. Then whatever design I have written, so you think about bigger designs, whether the design is implementing the proper operation or not. Then I have to test that. For testing that, we have next stage called as functional verification or design verification. So functional verification or design verification. So what is functional verification or design verification? Verifying this RTL code, whether it's functioning properly or not, whether it is implementing the intended functionality or not. That is called as what? Functional verification. So verifying functionality of design. Functionality of design is called as functional verification. Two, by using by using test cases. I want to I have written the program for mux. Right? I have written the program for mux. I want to know whether mux is working properly and what I will do. I apply different test cases. Test cases means here it's called as inputs. Apply different inputs and verify the outputs. All different inputs you have. Yes, I not, I one. I'll apply 0, 0, 0. What should be the output? What should be I? If select line is 0, I naught is 0, and I1 is 0, what should be my y? So y should take what? I naught only, right? What is I naught? That should be the output, correct? If 1, 0, 1, what is the output? 1, because my y should take what? I1. So this thing is called as test case. One test case. This is called as what? Another test case. So by applying different test case to the design, I will verify what output I am getting. Whether I am getting the required output, then my Verilog program is implementing the intended functionality. Whatever functionality we want, that is implemented in the RTL code. This is how we are going to verify the functionality of a design. So verifying functionality of a design by using test cases is called as what? Functional verification. See, to become functional verification engineer, you should be knowing system Verilog. There is separate programming language. System Verilog and Verilog both are same, but in system Verilog you have more constructs. How you have C++, right? All those constructs present in C++ is implemented in system Verilog. That you have to learn, and you have to learn UVM, Universal Verification Methodology, the strategy, how to do the verification of bigger designs. What is the test plan we have to implement? Next, now design is in what mode? Like it's in what form? Now design is in what form? Design is in the RTL coding, right? It is the RTL coding. It's in the what form? Behavioral form. So we are describing the circuit through its behavior. So now design is in the behavioral form. Is that behavioral form foundry can understand? This foundry can understand the behavioral form. No, foundry can understand only what? Layout of cells. First I want cells. Then I want what? Layout of cells. Cells means what? NAND gate, NOR gate, XOR gate. Next I want what? Layout of cells. Again, two steps is pending still. Right? My foundry can understand the behavior. Behavior is like a Verilog code like this. This Verilog code is called as what? Behavioral description. If statements, case statements, always block. Use all those things and we have to implement this. So to implement this, right, what we do is next stage is we will convert this behavioral description, whatever we have, this behavioral description, right? Next we'll convert to the gate level. That phase is called as synthesis phase. Next step is synthesis. What is synthesis? Converting RTL code into gate level netlist. I can tell gate level design, right? Convert it to gate level design. So now RTL whatever I have converted to what? Gate level. That is called as what? Synthesis. So who is going to convert this? RTL to gate level. Synthesis tool is going to convert. We are not going to do it. So even this we will do in our course. So converting the RTL into gate level netlist. So here we use a synopsis tool called as. So here tool use this DC shell. DC means the design compiler. By using this tool, we'll convert this RTL into gate level netlist. Even this we will do in the process. Now, can you briefly tell me what are the inputs required for this synthesis? What are the inputs required for synthesis? Be fast and tell me what are the
Yeah,
inputs
RTL
required.
code.
Good, very good, right? So one is RTL. RTL is required. This RTL only we have to convert. So one is RTL code. RTL is in what form? Behavioral form. But in the programming language, it is .v or .vhd. .v is extension for Verilog. .vhd is extension for HDL files. Extension will give. In Unix, will give all the extensions like .v is extension for Verilog. .vhd is extension for VHDL. .rpt is extension for report. .txt is a extension for normal text file. .tcl is a extension for normal TCL file. .sh is a extension for Unix file. Like that every file has their own extensions. So that my Unix having one editor called as gedit or gvim that can understand the syntax and it can give some color to that. For example, if I use a .v, my G editor will give some color. Module will be in separate color. Right? If I use module in Verilog, we have something called as what? Module. My G editor will use what separate color to each and every syntax using that based on the file extension what I give. If I don't give extension, nothing will happen. Only my tool will not give this color. That's it. There is nothing wrong with it. And if you give this file to any other person, he will first check for extension only. I want to identify RTL in group of files. What I will do? I will search with extension. .v extension which file is having. That file only is a RTL file or netlist file. So most of the files we identify through extensions, we designers, but not the tool. For tool, all the files are same. Only tool will utilize this extension to give what colors for the different syntax. Inbuilt syntax we have, right? Module name, input port, output port, all these are syntax. To give different colors, it uses this extension. That's it. Apart from that, there is no more use for these extensions. Only it is used for what? The designers to identify. So one of the input is RTL code. So it's in the behavioral form. Next, what is the input required? I want to convert this RTL to gate level netlist. Then who is going to give this gate information? See, convert this RTL to some gate level information, right? Then what gates I have to use to convert that? Whether for converting I have to use NAND gate, NOR gate, XOR gate, what gates I have to use? Someone has to give this
library.
information, right? What? So there is a file called as library file, liberty file. It's called as liberty file or library file. Right? It's in .lib format. So it has standard cell information. Right? What are standard cells? First of all, I'll define that. Standard cells are nothing but like, so it has like, first I'll let you know what is present in this. It has timing and power information of standard cells. I'll come to this later, this term. So what are standard cells first of all? What cells we call as standard cells? Something happened, wait. Standard cells. The standard cells are nothing but NAND gate, NOR gate, OR gate, AND gate, XOR gate, XNOR gate, MUX, flip flop, D flip flop, DFF. DFF means D flip flop. Then AOI gate, OAI gate. AOI means AND or invert. OAI means OR and invert. Next is you have like full adder, half adder. So all these things are called as what? Conductors, basic gates. Along with few gates like mux, D flip flop, all these are little bit apart from basic gates. So these gates, right? For these gates we have timing and power information. So this file is generated from a team called as library characterization team. We are not going to do that. There is a team called as library characterization team in industry. So they will do that. See what they will do. They will draw the schematic of NAND gate. You know what is schematic, right? Schematic means what? This is schematic. This schematic what? The schematic of inverter. So this PMOS, this NMOS, this is called as spice models. What is called as spice models? This spice models they will get from the foundry. They are going this spice models. The library characterization team like PMOS spice model, NMOS spice model. So all these spice models they'll get from the foundry. Like TSMC will give this. Why they'll get from the foundry? Because what is happening in silicon, right? That has to be mathematically modeled. That is called a spice model. Real silicon, how the circuit is behaving, that is mathematically modeled. So mathematical model of real silicon is called as what? Spice models. The spice models they'll get from the foundry. This spice, by using spice models, they'll create the schematic. For schematic, they'll apply different inputs. For these different inputs, they'll calculate what is timing and power. Timing means cell delay. What is timing? Timing means cell delay. For us, time cell delay is also very very important. So here timing means it is cell delay. So this library is technology dependent. Technology dependent means what? What do you mean by technology? If I tell 14 nanometer technology, what is the meaning of that? So you see the diagram here, right? The distance between source and drain. This is source, this is what? Drain. Distance between source and drain is called as technology. If I tell 14 nanometer technology, the meaning is distance between source and drain is 14 nanometer. If I tell 7 nanometer, distance between source and drain is what? 7 nanometer. For different technology, you will get different spice models. And by using the spice models, my library characterization team will create the circuit. They'll apply different inputs. For different inputs, they'll note down what is the output. From that output, they'll calculate what? Cell delay and power information of what? All this standard cells. And they will give in a file called as what? .lib file. So my synthesis tool will utilize this .lib file to convert what? RTL to gate level netlist. Next, one more file is important. What is that? One more file is very important. What is that? HDC file. HDC stands for synopsis, design, constraints. It is having a timing constraints mainly. I can tell timing constraint. The design means timing constraint mainly has what clock frequency. My design should work with what clock period. It's mainly having clock period. You know what is frequency, right? Inversion of clock period is called as what? Clock frequency. So mainly it is having clock period. With what clock period this entire design should work. Mainly that it has many other commands, but now for brief I can tell only clock period. It has having set input delay, set output delay, set driving cell. All those things we will study later in STA concept. Now I can tell clock period. Means this design should operate with what clock frequency. Right? That information is present in HTC file. See, doing synthesis directly is very easy, but with HTC, right, it's a little bit difficult. So, in the real synthesis, they implement various strategies, various techniques to meet this clock timing, to meet the power. They use different strategies again. Synthesis is not a one day work or one week work. It's 1 month work. Doing converting a bigger design into a gate level netlist is not a 1 day or 2 days work. It's like 1.5 month or 2 months work. So they have different strategies to implement all this converting gate level into netlist, RTL to gate level, right? They have different strategies again. So these are the basic inputs for RTL should convert into what? Gate level netlist. Then what will be the output of this? What is the output of this? Output is also a netlist, right? It's a gate level netlist. So what is gate level netlist? What type of file it is? It is also .v, Verilog or VHDL. Now there is a confusion, right? Even here RTL is also Verilog or VHDL and gate level netlist is also Verilog or VHDL. Then what is the difference between both? Good. Right? This is in the behavioral form. This is in what form? Structural form. See, this gate level netlist has only gates and its connections. That's it. In netlist, I should be not having any other statements. I should be having what? Only gates and its netlist. Only this information should be present in this. This is called this is the output of synthesis. This should be having only gate and its netlist. So what do you mean by net list? Right? I'll give one simple example here to show the net list. So you take this small design. So in this design you have one NAND gate. After that you have one OR gate. Next you have one NOT gate. This is the circuit what you got in the after synthesis, right? This NAND gate, its name is NAND2 in the library file. In the library file, what is the name? NAND2, two input NAND gate. NAND, not NAND. Sorry, it is AND. Right? Sorry, it is two input AND gate. And two. This is OR gate. Two input OR gate. This is inverter INV. What is the input here? I'll call input as like A1, A, B, C. Output as like out. Output is what? Out. These are inputs of the module. It's output of a module. So now this AND gate is having pins, right? A1 pin, A2 pin, Y pin. Inputs are A1 and Y, A2. Output pin is Y. OR gate is having A1 pin, A2 pin, Y pin, and this is having A pin and Y pin. Now this intermediate signal means the signal which is connecting from one gate to another gate, that is called as nets, that I will call as N1 and N2. Now how to write the netlist for this? So you know, everyone know Verilog, I think, right? You know how to declare Verilog. What is Verilog? Module name. Module name I'll take it as temp. And what is the inputs? A comma B comma C, and what is output? Out. So first I will declare inputs. Right? What are the inputs? A comma B comma C. What is output? Output is out. And next I have to declare the intermediate signals. What are that? N1 and N2 is wire. Wire N1 comma N2. Then how to write the netlist first? So for writing the netlist, right, first I should declare first a NAND gate library name. This NAND2 is the name present in the library .lib file, right, for the NAND gate. So first I write the library name. What is the library name? And 2. Next we should write its instance name. For example, this is the instance name U1, instance name U2, instance name U3. Instance name is given from synthesis tool separately. Because in the design I can be having thousands of AND gate, thousands of OR gate. So one OR gate to another OR gate, this should be different name, right? For that reason, my synthesis tool will give what? This instance name. Separate name for each and every cell. For AND gate, what is the instance name it has given? U1. The instance name given by synthesis tool. Next, we have port mapping. Port mapping means this A1 pin is connecting where? This A1 pin, dot of A1 connecting where? A port, right? Next, A2 pin, where it is connecting? B port, connecting to B port. Next, Y, where it is connecting? Dot of Y, connecting to N1 net. Right? Next, what is that? R. Next cell is R2. What's the instance name? U2. This A pin, where it's connecting? A pin is connecting to which net? N1 net. It's not connecting to Y directly, it's connecting through net. Right? Next, A2 pin, where it's connecting? C. Next, Y pin, where it's connecting? It's connecting to N2 net. Next, last what we have? Inverter. So this inverter, what is the instance name? A pin, where it's connecting? Into Y pin, where it's connecting? Out. So end module. So this is called as netlist. It is not having any other syntax, like assign statement is not there, if statement is not there, case statement should be not there, nothing should be present. It should be having only gate and its connection. See, gates are there, connection is also there, connection is there or not? Connection is there, right? This N1 is connecting to Y pin and this N1 is connecting to what pin? A1 pin. Right? This same N1 is also connecting to what pin? A1 pin. Then there is automatically connection, right? This Y pin is connecting to what? A1 pin of Y pin of your AND gate is connecting to A1 pin of what? OR gate. Because this net is output of what? AND gate and this net N1 is input for OR gate. Similarly, this one also, right? N2 also. N2 is connecting to output pin of what? Your OR gate and it's connecting to input pin of your inverter. Then there is a connection, right? This both is having what? This both is having connection. So connection is maintained. So in the netlist, we should be having gates and its connection. Only this much should be present in the netlist. Apart from that, no other information should be present. So after synthesis, the design is in the what form? After synthesis, design in what form? Gate level netlist. This gate level netlist we should convert into layout level. That is a role of physical design engineers. So, but in the real circuits, we will not be having only 3 gates. We will be having millions of gates. Means lakhs together gates. 1.5 lakh, 2 lakhs gates will be having. So we will be having gate and its connections for 1.5 lakh gates that we have to convert to the layout level. Because foundry can understand only the layout level. So that is the role of what? Physical design engineers. Next step is what? Physical design. See, before physical design, there is one more team called as a DFT team. Alright, that DFT team I'll talk after the break. What the DFT team will do. That is very important team. Alright. After that, there is a team called as what? Physical design team. But I'll only now discuss what is the role of physical design. Convert gate level design to layout level. Is the role of what? Physical design team. So, what is the content of physical design? So, what is the course content? What DFT will do? That we'll see after the break. We'll take a break. Now, time is 10:50. We will continue at 11 o'clock. Take 10 minutes break. Right? We'll continue at 11 o'clock. Okay.
This conference will now be recorded.
Yes, Sam. We will continue. Just we'll wait for 1 more minute. See here, and 2 indicates it is a 2 input AND gate. That is a library name. So if I have one more AND gate, the name will be AND 2 only. It's not AND 3. But this instance name is different. That is given by the synthesis tool.
So it is two independent input.
Number of inputs. See, this library name can be different also. It is library specific. Library designer is there, right? I told library characterization team is going to design the library file. They can give any name they want. It's not always they'll use AND. They can use only AN. AN 2 and they can give. Any name they can give. I've taken just an example. So next you have DFT. DFT stands for what? Design for testability. See what happens is when you fabricate the chip, right? When chip is fabricated, so you cannot tell that this chip is working. Foundries fabricate the chip, and you cannot tell that the chip is working properly because foundry is working in the watt scale. They are working in nanoscale. So this is the planar metal layer. For example, I have two metal layers running parallelly. This is a planar metal layer. This metal layer is formed by process called as etching. Etching means I will be having a full metal layer. I cannot create this much small metal layer only in this location. So I will be creating metal layer at this bigger location first. Then wherever I want this metal layers, right, I will cover through one mask. I'll cover through mask, only that region I'll cover through mask. Remaining all regions by using some photolithography method, I will etch it. Etch means remove it. Remove that metal layer. How to remove? Treat this metal with acid. Treat with what? Some high concentrated acid. This metal layer will get, yeah, means it will get erosed. Again, it gets melted and that will be removed. But this region gets unaffected because that's already covered through oxide layer. So only in this region I have a metal layer. So this creating a metal layer at this location is not like a grinding process, it's a chemical process. So when we have a metal layer both running parallelly like this, I cannot tell that these metal layer are fabricated properly. See, while acid erosion or acid etching, so you can be having metal layer like this. It's not completely planar. I'm telling in nanoscale, right? Remember, it's not, if we see in the centimeter scale, it is planar, but in the nanoscale, it's not planar. It is like this. It is like this. So without our knowledge, both of these metal layers are shorting here. This type of problem may happen in IC, but we are not aware. So when both are shorting, chip will not work properly. Obviously, there is a defect in chip. So when chip comes out of an IC or fabrication foundry, how do you tell that this chip is working or not? So testing this chip after fabrication is called as post silicon validation. Post silicon validation. So for doing this post silicon validation, right? My DFT team should implement some additional circuit in this design. They want some additional circuit to be put in this design so that I apply test vector and pass the test vector to this level. If I want to pass the test vector to this level, I want some additional flip flops or additional circuit to be inserted in the design. Those are called as those will help only for testing. So those circuits are inserted in the netlist by TFT team. They will insert during design phase only. That will help the testing of chip after fabrication. For that, the name called as what? Design for testability. Make the design ready so that the chip can be tested after fabrication. So testing the chip after fabrication is called as what? Post silicon validation. So testing chip after fabrication without affecting the functionality. That is the role of DFT. Right? Adding additional logic. Adding additional logic in netlist without affecting functionality, so that chip can be tested after fabrication. They have different methods again. What are the different methods they have? They have like ATPG, automatic test pattern generation. They have just built-in self-test. They have scan chain insertion. They have boundary scan. So all those things they will do, right? Uh, and this scan chain insertion is the main step after synthesis. They will do what after. See, this is done during front end ATPG and all. But scan chain insertion is done what after. Scan chain insertion is done after synthesis. They insert the scan chain. But so that netlist is not functionality is not affecting them in the netlist. Functionality remains same. They'll add some additional logic. Additional logic means additional gates they will add. The mainly they will do is scan chain insertion. That you'll understand what is scan chain insertion. That will cover in the physical design. So why DFT team is coming into picture? If they do all these things so that we can test the chip easily after fabrication. So once netlist goes to DFT team, they'll add some additional logic. Then it will come to what team? Physical design team. So when the design comes to physical design team, within what format? Gate level format. That we have to convert to the layout level. So now this netlist is having gate level, right? Gates, the standard cells, connection of standard cells. So for all these standard cells, I want layout also, right? Because I want to convert this gate level to layout level. I want even layout of this layout of cells. I want. So where we find layout of cells? Whether we are going to draw the layout, physical design team? No, we will not draw the layout. Physical design team is not going to draw the layout for all these gates. So there is a team called as layout team. They will draw the layout for all these gates, and they will give in a file called as LEF file, layout exchange format file. Format file. So in this file, we will get layout of all the cells. So dot lib is having what? Dot lib is having timing and power information of all the standard cells. And here LEF file is having layout of all the cells. So even we want dot lib also for physical design, right? One of the input is your dot lib also. Next is LDF. Next we have foundry rules. Foundry of some rules. Foundry rules is present in a file called as a TF file, technology file. Means what is the foundry rule? For example, I have two metal layers here, right? I have two metal layers. So between one metal layer to another metal layer, I should be having minimum spacing. I should maintain what? Minimum spacing. If I maintain the spacing less than this, my foundry cannot fabricate. And this metal layer, whatever I'm using, I should be having minimum width. If I have the width less than this, my foundry cannot fabricate. So like that, we have plenty of rules defined from the foundry. That rules we have to maintain during the physical design. And even my layout team is also done the layout for all these gates. Even they should also follow these rules. Is given in TF. So this rules is given from us from the foundry. These are the basic inputs what is required. We want netlist. We want what? dot lib, we want LEF files, we have what? TF. Still more, many inputs we have that we'll see in the things, what advanced classes, but basic inputs are these things required. So then what are the process happening in physical design? What we cover? Or what are the process happening in physical design? So first, first thing is partition. Second thing is, first we'll do the partition. Second thing is floor plan. So in floor plan, we have like create core area and die area. Next we have port placement. Next we have macro placement. Next power planning. Next third we have placement. Next fourth we have CTS. Next we have routing. Next is sign of text. Next is top integration, and that's it. So these are the different steps what we follow in what? Physical design. So first step follows what? Partition. See, bigger designs we cannot do physical design. Means one, if I have a design which is having 10 lakh cells, for 10 lakh cells I cannot do physical design at a time because it's very time consuming task. See, if I use one command in physical design, that will run for 2 days. The command itself will take 2 days to run because of, see, if I have only 5,000 cells, it will complete in 5 minutes. If I have 1 lakh cells, it will take 2 days. Imagine if I have 10 lakh cells, how much take? I am telling only one command to run. Like placement command I use or clock tree synthesis command I use, it will take 2 days to run. 1 lakh cells, it is going to take 2 days. But if I have 10 lakh cells, how many days it will take? It will take 4 days, 5 days, and 4 to 5 days you will sit without any work. The company will allow that? No. Right? So if you want to do physical design for 10 lakh cells, the first thing is the runtime is very huge. And to support this runtime, we internally we want memory, more core, CPU core, because number of calculations should be done inside. My algorithm will run. We want more RAM capacity, more core, more internal cache space we want. Then only my algorithm inside the tool will work properly. If I have more cells, if I have less cells, I don't. I want less resource. So for that reason, what we do is, if we have bigger designs, this is a bigger design as core area and die area, that we will partition into sub blocks like this. This we partition into sub blocks. One block will partition. So how many blocks I have? One, two, three, four, five. Five blocks I have. So bigger design we have partitioned into five blocks. This is block A. So each block owner will start doing physical design on each block. After doing physical design, all the blocks are integrated. So it is tested for final sign off and sent to Foundry. Create GDS and send Foundry. So now we are doing the physical design of each block. This is block B. So each engineer is responsible for doing physical design of their block. Now these blocks are given to engineers. They will do physical design for each block. So that step is called as what? That step is called as partitioning. Right? Partitioning is nothing but it's called as partitioning, right? So divide this entire full chip to different blocks, right? So Full chip is divided into different blocks. Next is floor planning. Floor plan. So now we are talking about this floor plan for which design? This block level design, right? So how to do physical design for this block? So that tip starts from here. From here, floor planning to sign up checks. So now I got my, see, for each block they will use separate netlist, separate dot lib, separate LEF, separate TF. In company there is a separate team called as top team. They will take care about dividing the blocks and giving these files. Now we are doing physical design for each block. Block level physical design we are doing here, right? So it is a block level physical design. So in block level physical design, the first step is what? Creating core area and die area. So in this we'll see how to create this core area and die area, right? We have core area. This is a core area, and outside we have what? Die area. So this is core area. This is die area. This is die area. So creating this core area and die area is the first step in block level physical design. So what is the different rules? So this core area and die area, we will get the information, how much core area to create, how much die area to use. So we will get the information from the top, right? Because top is reserved the area for us. I cannot create this core area and die area how much ever I want. A block level engineer. We should get information from the full chip level. So how much area he is reserving for me, that area I should use. Correct? So create this. So we will see in the design what are the commands to create it. So what are the different options we have to create it. So that is what the first step in floor plan. So next is port placement. What are called as what are ports? Inputs and outputs of a block are called as ports. Outputs of a block are called as what? Ports. Are called as ports. So next step, we will do this port placement. So in this we will learn what are the, even this port placement also is a guideline given from what? Top level. For example, my block A, all the output of block A is going to block B. You assume all the output of block A is going to block B. Then what will? Whether all the output ports of block A, whether you will place here, ports are simple metal layers, right? They will take the inputs from your block and they will pass the outputs. All the outputs of block A is going to block B. Then whether you place the ports here at the bottom? No, where you have to place the ports? We have to place a port on the right side, correct? Here I have to place. Then only my block A can take all the inputs. It can give all the outputs for what? Block B easily. Or sorry, not till this point. Even block B will be having, so input ports of block B should be present here. Input ports of block B should be present here. Now I can do what? I can do easy integration, right? I can easily connect them. Correct? So this port placement also defined from the top. So how this top is going to define the port placement? How to do port placement by taking the information from the full chip level? That we will see in the port placement. All the different methods, right? So here we are in the second step is port placement, right? In the block level, we'll do the port placement. These are all ports. So ports are placed in between core area and die area. So based on the guidelines given from the top, I cannot place wherever I want. I should follow the guidelines given from the chip top. Next is macro placement. So now till now I have not defined what are macros. I have only defined what? Standard cells. Then what are macros? See, macros are complex designs which are already optimized. For example, you assume that my block requires ALU. My design requires what? ALU, arithmetic logic unit. This ALU block is already designed from some other company. Some other companies already designed this. And they have also done the GDS. They also have GDS. They also has LEF file. They also has .lib file for their block, for this ALU block. So now, when you will think whether directly purchasing from them is good or you creating that from the scratch is good. Means you creating from the scratch means for that ALU block you have to write the Verilog code. You have to send that to what? Synthesis. Then you have to do physical design. That ALU will be found by using different basic gates. I have a ALU block. The inside is ALU. I will be having what different basic gates. Layout of basic gates. I have to connect them. I have to see that this ALU is working in the better performance with better performance. So instead of doing that, I am my one of the designer is telling that I have ALU, which is doing the better performance, best performance. Then what I do instead of I doing from the beginning, I directly purchase the layout information from him. That layout I will keep in my design. This is a ALU layout. So my effort is reduced. So in the market, everyone of polyogramics, MTR polyogramics, GRD polyogramics, or Assam powder mix. So what you are doing there? You are directly purchasing from the shop. Your effort is reduced. Doing from the scratch. The same way the macro, right? Your effort is reduced there. Correct? So macros are nothing but complex designs which are already optimized. So if you feel that in your design you want something which like that, you can directly purchase from some other vendor and the layout information that you can directly use in your design. That your effort is reduced in writing Verilog code and synthesizing some part of design. And second thing, some of the analog blocks where we cannot write the Verilog code and do synthesis. There are few analog blocks which we have to use. For analog designs, we cannot write Verilog code. We can write Verilog code only for the digital design. Please remember. Digital design means the signal has only two values, logic 0 and logic 1. Only those type of circuits we can write the Verilog code. We cannot write Verilog code for the analog designs. What are the examples for analog designs? PLL, amplifiers, ADC, TAC, all these are analog circuits. If any analog circuit I want in my block, then I cannot write the Verilog code and I cannot synthesize it. Directly I will purchase the layout of that analog block in my design. That is a macro now. So do that macro placement first. If you have any macros, do the macro placement first. Why macro placement first? Because macro is a bigger design, sir, not a smaller design. Their layout is very big compared to what? Standard cells. So reserve their areas first where they have to be placed. Then secondary thing is macros are less in number compared to standard cells. Standard cells will be in lakhs, but macros will be in hundreds or 200s, below 150, not more than 150. So do the macro placement at the beginning, right? You will do the macro placement now. So all these are macros. This is a layout of a macro. This layout we are not trying, we are purchasing from the third party vendor. So these macros are also called as IP core, intellectual property core. It's their intellectual property, we are purchasing it. So this is a macros. If we have anything in the design, we will place them first with some rules. So macro has special rules to be followed. So we will study what are all the different guidelines for macro placement in our design. So how to do the better? See, macro placement is a major aspect in physical design. If macro placement is not good, entire design will fail. So what are the guidelines? What guidelines we have to follow to do better macro placement? That we will study in this macro placement of floor plan. Next is power planning. See, you see the layout here, right? This layout, whatever I have drawn at the beginning, this requires what? VDD and ground. All the standard cells, 1 lakh standard cells, what I have here, all the standard cell layout requires what? Power and ground connection. So plan the power in such a way that all cells are getting power and ground connection without IR drop. Right? So power planning mainly focus on supplying, connecting VDD and ground for all cells and macros, but out with less IR drop. What do you mean by IR drop? Then what is IR drop? For example, I have one cell here, and this is my VDD port. Assume that this is my VDD port. I am getting a connection from here to this cell. VDD I am connecting here. Here VDD is 1.5 volt. So at the lower technologies, the VDD will not be 5 volts or 2.5 volts. It will be 1.5 volt only. So this 1.5 volt, whatever I have, right, it's at the port. But when it reaches to the cell, right, that will reduce to 1.2 volt. Zero point 0.3 volt is lost. Why? Because this metal layer, whatever we have, right, it has some internal resistance R. This connection happens to metal layer only, right? So and current is flowing. When this cell is switching, means logic 1 to logic 0, it will draw the current. When the current is drawn, this metal layer is going to conduct what? Current. So current is flowing. So V is equal to what? I into R. This I into R is going to have some IR drop. So this metal layer is having zero point 0.3 volts IR drop. Out of 1.5, 0.3 is going on what? Metal layer. And remaining how much is reaching to the cell? 1.2. See, I cannot reduce this. See, how to reduce this IR drop? Reduce the resistance, right? If you reduce the resistance, resistance reduces, voltage drop also reduces. If this voltage drop reduces, entire voltage, whatever I have, that will come to what? Cell. If I have 1.5 here, all 1.5 will come to the cell, near to the cell. But I am not getting 1.5, I am getting only 1.2 because the voltage drop is happening on metal here. How to reduce IR drop? Reduce the resistance of a metal layer. How do you reduce it?
Length of metal layer.
Reduce the length of metal layer. You use more width. So do the power planning properly to accommodate all this current and to reduce the IR drop. That power planning we learn in this stage. Right? How to do power planning to have the less IR drop. So that see if this IR drop is if the less voltage is reaching, what problem you may face? For example, instead of 1.5 volt, you are getting 1.2 volt. What problem you will face in the real design, in the real circuit?
Timing delay. Delay.
Yes, very good. Cell delay reduces, right? Cell delay is going to reduce. See, you know CMOS cell delay is what? Mu n C naught of x W by L VGS minus VTH the whole square. Here VGS means what? Nothing but VDD only, right? If VDD reduces, current reduces. Current reduces, cell delay increases. So cell delay is going to increase if you have less VDD. So how this voltage is going to affect cell delay? How this voltage is going to affect your power consumption? All those things we are going to learn in CMOS basics. For that reason, only CMOS basics is important. If you are not knowing how voltage is affecting your cell delay, so then your CMOS basics is very important. That course, right? So this is called as power planning. So plan your power properly in such a way that you are not having more IR drop. You are having only less IR drop on metal layers. So that entire voltage is reaching to the cells that you are seeing there. So next in the placement. So floor plan gets complete now after doing power plan. So how to do power plan? If I explain also like it is of no use, you will learn anyhow in detail what is power plan, how to do power plan. Right? Next is placement. What is placement? So placement of standard cells inside a core area is called as what? Placement. See, I have millions of standard cells, right? That millions of standard cells I should place inside this core area. Standard cells are very small. They are not very big. Compared to macro, they are very small. So I'll write here like these are standard cells. Start placing your standard cells. These are standard cells placed inside this core area. So while placing standard cells, you should see that there is no congestion, right? All these standard cells are routable. I should get sufficient space so that all cells are routable. That is called as congestion. So see the place the standard cell so that the timing is met, right? The placement should happen with less congestion, less timing violation. So what are all these things? What is congestion? What is timing violation? So all these things you will learn in the major means physical design advanced part. So less congestion, you should be having less timing violation. So to understand this timing violation, right, STA is very, very important. So here we will also cover STA, static timing analysis course. So what STA covers? So you will learn what is cell delay, what is transition, and this will depend on what parameters. Next is dot loops. What is a dot loop content totally? So how the timing is developed. So next you will study what is Q, latency. Next, setup and hold violation. Here you study latency, Q, latency, uncertainty. Next, you will see what are different modes, corners, and scenarios. Next, you will see what is. So just I'm mentioning what the topic is covered. Right? You can understand only when you go to the topic. Next, you will see what is multi-cycle path, false path. Next is right, asynchronous timing analysis. These are the major things covered in what? STA. So all these things, right? After studying STA, you can see that whether you are having timing violations or not. The placement. So placement, doing placement is not straightforward. Place and inside the core area. You should place such a way that it is having what? Less congestion. Congestion means whether all the cells can be routable or not. You will evaluate that. Routable means they can be connected or not through metal layer. Then you will evaluate whether they are having less timing violations or not. So majorly here we will do setup analysis. We are going to evaluate them. These are the main things in placement step. So STA is not only done at the placement stage, it is done each and every step here. So first we will, before placement, we will do what? STA. Because before starting the placement, right, you should be knowing what is STA. So I will put this topic here. In our course, we will do STA before starting placement. So one more technique, one more thing also we do here. One is low power techniques. We also cover low power techniques, which I have not covered in the flow, but here I'll mention that. What are the low power techniques covered? Means to reduce the power, what are the techniques we can follow in physical design? Right? The first thing is power getting design. If any block you don't want, that you can turn off. So the power is, your laptop will go into sleep mode, right? Same way, any block you don't want, you can cut the power to that. That is called as what? Power getting design. So multi voltage design. So use a different modules with different voltages. That is called as multi voltage design. Next is multi VT cells. Next is clock gating design. So these are different power reduction techniques we will decide. This is the topics where is given to 4 plus or 5 plus year engineers. Even that we will cover in this course. Right? But you have to utilize in effective way. Right? That you should can put in the resume that I have done this. Then you should be in a strong enough to answer that in the interview. At least if you learn what we teach, right, that is sufficient. But you should be focused on that. See, focusing, projecting yourself that you should do it. I know this, I have learned this. Each and everything what we have learned, we taught you, if you project that properly, right, you see, company will not take you as 3 plus or 4 plus years directly, because they, apart from the course, they will also see your previous background, like whether how, what company you have worked, show me your salary slips, all those things they will ask you. So because company wants to pay you always less, they don't want to pay you higher package suddenly. Right? So they will find one more other parameter to do that. But the course content what we have, that is equivalent to 3 to 4 plus years experience. That you have to project to that level. So you have to handle the interview confidently after learning all these things. Then you can easily go to 3 plus or 4 plus years experience. So these are the two aspects which I left in floor planning. One is low power design that we cover in floor planning. Next is STA. It's not done in floor planning. It's a theoretical concept which we apply in each and every step. Right? Next is CTS. So CTS stands for what? Clock tree synthesis. So what is clock tree synthesis? Build clock tree by using buffers and inverters. Why we have to build a clock tree? Now my question is, why we have to build a clock tree? What happens if I'm not building clock tree? See, I will be having a one clock port. Through this port only the clock will be coming to my plug. And only this clock will be driving how many flip-flops? Thousands of flip-flops. This port only will be driving to how many flip-flops? Thousands of flip-flops. There is a direct connection. See, whatever standard cells I have placed here, right? These are all layout of standard cells. You understand? I have written only box, but inside that box is what is present. Layout is present. So we are placing layout of standard cells. Right? Now, this is this port is connecting to all the flip-flops. Like this. Now, what is the problem when we connect this only one port to all the flip-flops? See the load on this port, right? The capacitive load on this port get increased. See all this flip-flops, right? They'll be having pin capacitance. See, flip-flop means input, right? Input is having pin capacitance. If you see this CMOS structure, you have a capacitance here. Top you have what? Positive plate. Here if you see positive plate. In between you have what? Silicon dioxide. At the bottom you will be having channel, that's a negative channel. So there is a parallel plate capacitor formed. Right? So that parallel plate capacitor at the input side is called as pin capacitance. So every input pin will be having pin capacitance. The sum of pin capacitance will become what? Load capacitance for the previous cell or the previous port. This load capacitance, we are not connecting it. It is found by virtue of its nature. Or sum of all the pin capacitance will become what? Load capacitance. If the capacitance here is 1 Fermi farad, if I have 1000 flip-flops, it becomes how many Fermi farad? 1000 Fermi farad. Right? Because sum of all the flip-flops is going to become the load capacitance. So what is the total capacitance here? 1000 Fermi farad. So huge capacitance. Now, if I tell the clock is becoming logic 1, this is the ideal thing. Right? But ideally, really, the clock will not become logic 1 like this. It will take some time to become logic 1. It will take some time to become logic 0. Why this transition is there? Because this capacitor should be fully charged. Then only it is called as what? Logic 1. This capacitor is fully discharged. Then only it is called as what? Logic 0. If this capacitance load is very huge, then it will take more time to charge, right? It will take more time to charge. It will take more time to what? Discharge. Then where is the clock signal here? Clock signal has become what? A triangle signal with no pulse at all, right? On pulse is not there, off pulse is not there. This is a problem with if I use this structure. So then what we do is we will start reducing the load on the clock port by building the clock tree. So how do you reduce the load? If I tell the principal, right, you only go and tell that one information that tomorrow is holiday to the college today, right? It will take how many hours to do? Right? What he will do? He will send all the information to the what? HODs. HODs will send to class teachers. Class teachers will send to what? The students' ultimate load. Right? The load is reduced. The information is also passed very fast. Similarly, here also, right, we have anchoring buffers first. So this port is now not driving how many buffers? Only 3 buffers. Now what is the load I have? Only load of 3 buffers. And this buffer is again driving 2 other buffers. And this buffer is connecting here, and this buffer is. So from here to here, I have more length, more net length. Net length is also having net capacitance. That will also create huge load on this buffer. To reduce the load rate, again I will use one more buffer here. Means to reduce the net length. More net length, again more capacitance. So on this buffer, again I will be having more load capacitance. To reduce that, I will use one more buffer. So this I can directly connect here. This use one more buffer, connect here. Here use one more buffer, right? Connect here. So this buffer, right? I can connect here. This I can connect here. So more net length. I should not be having more net length. Even that will also create net capacitance. That net capacitance will become again load for the previous cell. Again use like this. Connect here. Again use one more buffer. Connect here. Connect here. So I have built a tree by using what? Buffers and inverters. So instead of using buffers, I can use what? 2 back-to-back inverters. So why we are building a clock tree? To meet what? Clock transition. So I will define the clock transition should not be more than some value. This transition should be less than some limit. I will set the limit. So the designer will set the limit. My tool will try to meet this transition. If transition is less, what happens? I will be having more on pulse and I will be having what? More off pulse. Now I will be having a clock signal ideal to the clock signal like a ideal signal. So this rise transition and fall transition the designer is going to mention during clock tree synthesis. So clock tree synthesis is mainly done to meet what? Clock transition. To meet clock transition. See, to meet clock transition, right, my tool should not insert more buffers. Correct? If it's inserting more buffers, what happens? The clock edge which I am getting here at 0 nanosecond, the same edge will reach this flip flop after few nanoseconds. Because I have in between, I have what? Buffer delay. Correct? There's a delay in reaching the clock signal. Delay in reaching the clock signal to the flip flop is called as latency. So the latency will increase. Right? So I should be having less latency. What is latency? Delay in reaching the clock signal to the flip flops. So I should be having less latency. Next, I should be having less Q. Q means delay in reaching the flip flops between two, delay in reaching the clock between two flip flops. For this flip flop, the clock is reaching early because it's near to the port. It's reaching at 1 nanosecond. For this flip flop, the clock is reaching at 3 nanosecond. What is difference in clock reaching? 2 nanosecond. The difference is called as what? Skew. There should be no difference than some limit. Difference should be less within some limit. That we have to meet. So we should be having less Q. So we should be having less latency and we should be having less Q. That is the major goal of what? CTS. Meet the clock transition with what? Less latency and less skew. So after building clock tree, next we'll do final routing. So what is routing? Connect all cells by using metal layers. This is called as what? Routing. So you have all the cells, right? These cells. You start connecting by using not only cells, connect all cells, ports, and macros. Macros by using what? Metal layers. So start connecting them. So my tool is going to follow what connections? The connections present in the netlist. How the connections present in the netlist? That output pin of this cell should connect to input pin of what? R-gate. What connection present in the netlist? The same way start doing the connections. So this is called as what? Routing. So not only cells, right? You should also connect what? Ports. You should also connect the macro output to the cells. So after routing, we do sign off checks, right? So after routing, mainly we do here only we do different checks. One is a DRC, right? Design rule check. What is a DRC? Design rule. Design rule check means while doing this routing, whether I am following the foundry rules or not, right? And it's called as what? Design rule check. So foundry rules is present in which file? I already told at the beginning, right? The foundry rules is present in a file called as what file? TF file. So while doing this routing, right, I should follow the foundry rules that between one metal to another metal I should be maintaining the spacing, and the metal I should be using minimum width. So YR rules will be there that has to be followed. So many rules should be followed during doing this routing. So that check we will do, that is called as what? DRC check. Next we will do LVS. LVS means layout versus schematic. So what do you mean by layout versus schematic?
Requirement basis how we have to follow.
See, you have the layout here. This is a layout. What is this? Schematic. What connections present in the schematic? The same connection is maintained in the layout or not. That we will cross check. That is called as what? Layout versus schematic. So check the connections in the layout with connections present in the netlist. That check is called as what? Layout versus schematic. If same connections are maintained, no issues. If same connections are not maintained, then you have to debug what is the problem, why it is not maintained, where it went wrong, whether there are any shorts. Okay, this two cells are having connections, and this cell is having connection. I am going like this. Then what happened? Here there is a short, right? Both are same metal layers connecting each other. There is a short. So this short I can see in LVS. So here unnecessary connection. So A and B cell should connect. This A cell and B cell, and C and D should connect. But what is happening? C is also connecting to what? A. This unnecessary connections is seen in what? Layout, but that connection is not seen in netlist. Then there is a shorts present in the what? Layout. So for example, this E and F cell should connect to each other, but for some reasons they are not at all connected. They are left unconnected. In the netlist there is a connection, but in the layout there is no connection. Then this is called as opens. So you will study shorts and opens after LVS. So why there is shorts, why there is opens, what are the reason for that, how to fix it. Shorts and opens are analyzed. So whatever I discussed now till this floor plan, till routing stage, this is called as PNR. PNR means placement and routing, including floor plan also. This is called as what? PNR, placement and routing. This is done by a tool called as ICC2 tool. Right? Here we use from here, right? We use a tool called as tool ICC2 tool. ICC2 stands for Integrated Circuit Compiler 2. Earlier there was a version 1. Now we are using Integrated Circuit Compiler 2 tool. Right. So after routing, we will do sign off checks. Sign off checks means the final check for the block. Whatever the block we have done. So first we do power and IR drop check. How much power my tool is consuming, right? IR drop check. What is the total IR drop? What is the maximum IR drop happening? IR drop I already discussed, right? Which cell is showing more IR drop? So this is the power and IR drop check we do. There is a separate tool called as radar tool. And second thing, we will do STA, static timing analysis. Here also we can do STA, each and every step. After placement we do STA. After CTS we do what? STA. After routing we do what? STA. Again separately we will do in a separate tool called as prime time tool. Thus, this tool is very accurate compared to ICC2. ICC2 also does STA, but prime time is very accurate. Again, we do this STA for this design by using what tool? Prime time tool. And next we have one more check called as physical verification. Again, right, in physical verification, the same thing we will verify DRC and LVS, but this tool is very accurate. More rules. This tool is going to verify more rules. The same DRC and LVS check we will do here. So when this block is violating all the sign off checks, when it is passing all the sign off checks, then we'll send for chip top team. It's not only called as top, chip top. So they will do the integration of all these blocks. They will do integration of all these blocks and they'll send to foundry. right? So this is the process of physical design. So here we will cover from this point till this point, till partitioning. So as I told, we are using IGC2 tool. Which tool we are using? IGC2 tool, and we are using for sign off, right? Prime time. So here we use IC validator, use caliber. We are using all the EDA tools. So I have already told you EDA tool is going to work only on what? Unix operating system, right? Mainly we'll install in Unix operating system. So to handle that work environment, to create the folders, to copy files, so to have some file permissions. So to learn to do all these operations, right? You should be knowing, which I already discussed at the beginning. You should be knowing what Unix. Next, to interact with these EDA tools, you should be knowing what TCL. So now in this explanation concept, you undergone many CMOS content. So to understand entire CMOS content, you should be knowing what CMOS basics. So I already discussed earlier. First 2 months is what basics. Next 3 months is PD advanced course. So PD advanced, we'll be giving 2 projects, and project will be done on Monday to Thursday. Friday is off, and you can also opt for what Saturday and Sunday project sessions. But theory will be always on Saturday and Sunday. It is for both the weekdays batch and for weekend batch. For them, theory is a common time, and basics runs for all the days in a week except Sunday. Monday to Saturday you have basics. First basic starts with digital. So here one more thing I have mentioned, I've forgotten the Unix GVM basics. I'll mention at the last one. GVM basics. GVM is a editor. So what editor I'm using here? Text editor, right? This editor can be used by using separate editor called as GVM editor. This editor has many advantages compared to normal text editor. Right? So what are the how to use this GVM editor? What are the commands to use? What are the commands to copy from one GVM file to another GVM file? How to open two GVM files in one window? Right? How to delete any line I want to delete? How to delete here? How to delete here? For example, I open that file. Wait, I am not sure whether. Okay. If I want to enable the line number in normal file, what is it? So you will enable. So here there's a command, right? Escape colon. Okay, this file is a normal file. Sorry. Okay, I have opened the file. I want to enable line number. What I should do? Set escape colon set menu. I got what? Line numbers. I want to delete 20th and 20, 18 and 20th line. What I'll do? I'll press here to D. I deleted. Line got deleted. Didn't do anything, right? So I'll just type 2D. 2DD. Line got deleted. So like that, right? Out. What are the commands to use this GVM? So GVM, using GVM when you become expert is easy. So that you will learn even in basics. So all these things are very, very important for us. Okay. So now we focused on why physical design. So why physical design? From synthesis stream we get what? Netlist that we have to convert into gate level, sorry, layout level, and that layout level we can take GDS, that then we can give to what? Foundry. Foundry will fabricate IC for us. Then what is done in course content, right? We'll cover from floor plan to routing stage, including STA with the two projects. Right? One project is done with help of mentor, another project will give to you people to practice it. So along with that, we will also do this prime time timing sign, power sign off, and physical verification content. That is your course content. So if you have any doubts now, you can ask me.
Sense.
See, macros from our point of view, it is only the layout. We cannot see what is present inside the macro, right? Because that is a hard IP, hard macro. Hard macro means the functionality or cells inside the macro we cannot see. We can only see the layout. But that person, those who are creating the macros, they would have followed any method. For example, analog macro, they will directly draw the schematic. Schematic they will directly draw because they cannot do write the Verilog code and they cannot do it. If you purchase analog macro, they will draw the schematic of A to D converter, or they will draw the schematic of your PLL, and they will draw the layout for that and they'll give to us. When we purchase a digital macros like memories and all, obviously they will be first they will be writing a Verilog code. They will be doing all the steps whatever we have done. They'll create the GDS and LEF file and they will give to us. So that inside that there can be a macros, sorry, inside that there can be a cells, but when it reaches to us, we cannot see what is present inside that. We can only understand that is a layout. That's it. But some companies will reverse engineer that. If they wanted to understand that, right, they will do reverse engineering. Like from the layout, you understand what is the gates present. So that is even some companies will also work on that. I cannot comment on that. But macro is a hard IP. Hard IP means we cannot see what is present inside the understand what is present inside the macro. They'll not leak that content, right? If they leak that content, everyone can do start doing that. That is a patent actually. IP means it's a intellectual property. They already done the patent of that macro. See, you do one design today and you see that tell that your design is having a better performance and is having a better showing good results. Then you can make a patent of that. So you can also send that for silicon testing. Like you can send the foundry, you can do the silicon testing. You need not get it fabricated for market purpose. You can do silicon testing. Then you can sell your GDS file, LEF file, right? Then .lib file so that you can utilize that. So IP cannot be only hard IP. IP can be also soft IP also. Soft IP means if you write some Verilog code and your Verilog you can write Verilog code, very good Verilog code, and you have written the Verilog code for ARM processor. And if you give this if you sell this Verilog code, Verilog code becomes soft IP because that inside the Verilog code what is present they can understand. Right? That is called a soft IP. Even you can sell the Verilog code also, it's called a soft IP. But for physical design level, if you get soft IP, no use. We should get what? Hard IP. If you get soft IP, again we have to go through the process of what? Synthesis, physical design. We should go through that process. But only writing the Verilog code burden is reduced. Purchase. There are companies even who produce only soft IPs. Right? Verilog code. If you, for example, any person will ask, I want this type of protocol to be written, and it has to be tested in these two processes, right? This like the RTL specification, RTL code, and functional test. After doing this functional test, they will release that code. It's called as what? It's called as soft IP. After doing synthesis, if they release, then it is called as firm IP. Means they are already mapped to the cells. They cannot change the functionality now. At the bigger level, they can change one or two cells. The functionality cannot be changed. At the RTL level, functionality can be changed. But when it comes to the physical design, right? If physical design only needs gets what layout, right? Then it is a hard IP. We cannot do anything changes inside that. That is called as IP or macros. Yes. Any other doubts you have? So in this course, even this synthesis is also covered. So I forgot to tell that, including physical design, even the synthesis is also covered. How to do synthesis, because it's a previous step of physical design, right? You should be knowing how to do synthesis. So even that 2 days of class will do on synthesis also at the last. How to do how the netlist is formed, what from the tool. It is hands-on again, right? Not the theoretical. Okay, what are the placement, right? Placement means you already know there are the top product-based companies. What are product-based companies? Intel, Qualcomm, AMD, Nvidia, MediaTek. Those are called as product-based companies. Product-based companies will not hire the employees directly from the colleges. They only hire from top colleges or 3+ years experience. More than 3+. Freshers they will not hire suddenly. They'll hire from NITs and IITs. But below product-based companies, there are many companies called as service-based companies. These service-based companies will work on the projects of product-based companies. So these service-based companies will hire even freshers, but you will be working with the projects of what product-based companies. For example, you are part of one company and you will be doing the project of Intel. You will be doing the project of Qualcomm. So when you become 3 to 4 years of experience, even you have a chance to get into what product-based companies. So many are working in product-based companies from VLSI group. Right? See, this is not because they not hire from VLSI group. They not hire from any freshers. They not hire. They'll hire only 3+ years experience. See, product-based companies will never invest a single rupee on training. But so service-based companies will invest on training. Service-based companies that take the candidate, they'll train to like 1 month. They'll train what is a this training is sufficient. Just they'll train the corporate training. Corporate training means so if they ask the project, they'll showcase any candidate has 3+ or 2+ years experience. What if they ask what project you have done? You answer this one. The company terminologies they'll tell you, and they will make you to work on the product-based companies project. So when you become 3+ or 4+6 year experience, even you have a chance to get into what product-based companies like Intel, Qualcomm, AMD, right? You can get in. And we have one more recent news that India signed a MOU with Tata for opening a fab in India only. So till now we don't have any fabrication unit, foundry, right? But now India is thinking to start a fab in India itself. We have fabrication units, but not well sophisticated. It's for only research purpose. For production purpose, we don't have any such fabrication units. That is foundry. So India is now, they have already signed in the budget also. They have already processed that with the contract with Tata groups. I think the new thing you have seen. If that is going to happen, right? Even the see when the product based when the foundry is there, then it becomes easy for our Indian product based companies to get the IC done with less cost, because now all the Indian companies has to communicate in terms of dollars only, right? Now they can communicate in terms of rupees, even can get done with lesser cost. Even production in India may also double. Even they may hire more VLSI engineers. There's a chances if the foundry or fab is going to open in India. So that is also one of the good news for VLSI engineers, that fab will be established in India itself. Very good fabrication unit. But as I already told you, we don't have any role in foundry. But if foundry is established, right, we design process may increase in India. Number of design units may increase. So they may hire many number of engineers. Yes. Any other doubts? So if you don't have any doubts, right, you can leave. Right, that's the end of your demo session. If you have any doubts, you can ask. So I will wait for another 2 minutes. You can ask. So I'm not getting any questions from online, right? Any doubts? So starting off the course, probably it will be from Tuesday or Wednesday. They've informed you. So they'll inform you it will be from Tuesday or Wednesday. Basics.
Sir, starting of the course from what date, sir?
Tuesday or Wednesday. Okay, let's confirm that. One second. Manor.
From next week onwards, sir.
Yes, Tuesday. It is from Tuesday, coming Tuesday. Day after tomorrow. Okay, the course is also available in two modes. You can attend online or offline. Now, how it is happening, right? Few are attending online, as few are attending offline also. Same way, at a time, it also happens in online as well as offline also. So you can attend in any mode you want. And record video is available for both on and offline. So to give the record videos, it will take 4 hours time after course completion, because it has to be uploaded in the server, then they have to download it, and they have to put in the website what they are giving to you. So that takes some time. That is 4 hours you have to wait to get the video. Yes, Aishwarya, you can ask me. What is your question? Do you have any question? You have raised your hand. Yes, any doubts you have? So tool access is given after 3 months, 2 months. After basics only, they will give you the tool access. But when you enroll for when you enroll for advanced, they'll give you the tool access. When you enroll for basics, right? First they will give you the tool to use this basics. Like they'll give you the Sigwin, some other tools. Later, when the time advanced starts, right, they'll give you the advanced tools. HC2 and design compiler. But currently, if you enroll directly for advanced, the tool they'll give the tool according to your requirement. Yes, then thank you everyone.